This is a help video for the Laplace Mesh Solutions game in Circuit Tutor Level 2. So we're going to go ahead and go into that game. And you should, of course, have watched the introductory, or have rather done the introductory tutorial under the Laplace impedance simplification game, which provides lots of important information for completing these exercises. So having assumed that we've done that, it's always a good idea to look at some examples here before starting to try to solve the problems yourself, so that's strongly recommended. In the interest of time, however, I'm going to go straight into a problem. So this is a level 2 problem in in Laplace Mesh Solutions. So we have a couple of resistors, a couple of independent voltage sources in this case, inductor and a capacitor, and the sources are of the step function variety. So our first step here will be to convert this time domain circuit, where we have farads and henries and time, into the Laplace domain circuit, where we have only ohms and S variables. We do not have any time. So first of all, we'll convert the independent voltage source here, which is 2u of t. So that becomes 2 over s, using the standard Laplace transform of a unit step function. And hopefully you remember that, but if not, you can look that up on the Laplace transform table at any time. Then for the capacitor, we remember that the capacitive impedance is 1 over SC. So that's going to be 1 over quantity 3s here. And the parentheses are essential to make sure that both the 3 and the s are in the denominator. Now the 2 Henry inductor, remember the inductive impedance is SL, so that's just going to be 2s, or S2 if you prefer. And finally, for the other voltage source, again, this is the 6u of t, so this will simply be 6 over s, similar to the other one. Okay, so having entered all of that now, we just click Done Converting, and those values are correct. So the next step, as always in a nodal analysis, is going to be to, in a mesh analysis rather, is going to be to pick the reference mesh. If you're not familiar with the concept of a reference mesh, that's something that would be discussed in the DC mesh equations tutorial in Circuit Tutor. Here I'm going to assume some familiarity with that. So our reference mesh ideally should be one that's connected to a lot of current sources. So here we only have one current source, which is the 6IS, so that 6IX. So that should be either here or here. And we also want a lot of elements there to minimize the complexity of the equations we have to write. Since we won't write one for the reference mesh, we prefer to have more elements in that mesh than in the other one. So this would be sort of the optimal reference mesh. So I'll just click there, placing our halt symbol, which indicates that that mesh current is set to 0. In conventional practice, one always takes the outer mesh to be the reference mesh without even sometimes stating that. But here, as I said, this will be a little bit advantageous for us. So we'll click OK then. And now it'll redraw the circuit with the mesh currents shown using that reference mesh. We have our instructions here. And we can look at that also if we need help entering any of the expressions for rational functions. The syntax guidance document is here, and that's always accessible from the help menu by clicking on the help button here and then clicking on this button. Most of the time it'll give you feedback to tell you if you're doing anything wrong, but if you need it, you can look at that. Okay, so now we have our clockwise mesh currents on the 2 interior meshes that are not the reference mesh, which is I2 and I3. And then we have a counterclockwise mesh current on the outer mesh. Remember that the outside of the circuit is also a mesh. And that one, we want all of our mesh currents and adjacent meshes to be going in opposite directions. So that's why this has to be counterclockwise, where the interior ones I've chosen to be clockwise. So we'll begin here by writing, since we do have a current source, we will need to write a current constraint equation in mesh analysis for that. So we'll select that option. And we only have one current source, and there's only one mesh current going through it, so that will be this term here equals a fixed value of that, or I'm sorry, it's not a fixed value, it's 6IX, so we need this term here, which is for a current controlled current source. And so the I2 is in the same direction as that, so we'll have I2 here, and then this will be a plus sign because they're in the same direction as opposed to opposite directions. And here we'll have the gain, which is dimensionless, the 6 amps per amps, if you will. And then the alpha gets replaced by the control variable subscript, which is x. So we check that one now, and that is correct. And next we'll proceed to the KVL equations, which are the sort of core equations for a mesh analysis, which is based on a systematic application of Kirchhoff's voltage law. So we'll select the KVL equation type, and it asks us which mesh or meshes we want to write this for. So first of all, for mesh 2, we see that one we cannot write a KVL equation because it has a current source, and we don't know the voltage across current sources. It's going to be whatever it needs to be, which we don't know at this point. So we don't, however, have to write that because we already have a current constraint equation for that variable. So we'll instead go to mesh 3. Now this one has no current source, therefore we can and should, in fact must, write a KVL equation for that mesh. So I'm going to select mesh 3 here. I could do 1 first, but I'm just going to do 3 first. And now I'm going to go clockwise in the direction of I3, which is a convenient thing to do. So first we're going to have an impedance with 2 mesh currents, so that will require that type of term. And then again, this impedance also has 2 mesh currents. And then finally we have a fixed voltage value, so that will be just this fixed voltage term. And some of those 3 elements then will, or 3 voltages rather, will be equal to 0. So now we'll fill in the blanks here. So in this case we have I3 minus I2, since that's the net current going in the direction that we're traveling, which is clockwise, and we're going to use passive sign convention to add a voltage drop here. And that's across the 2S impedance, so we enter the 2S. And the next one would be across the capacitor here. So now the first current is going to be the I3, and then the current going in the opposite direction would be I1, so we have to subtract that to get the net current going to the right for that drop. And then the impedance is the 1 over 3S. So we type 1 slash, and then we have to have parentheses around the 3S to make sure that both 3 and S are in the denominator. And then finally we have this fixed voltage value, which is just the V1S value, which is 6 over S. So we'll just enter that value, 6 slash S. And that completes the equations. Now we'll check that. And that is correct. And now the I1 mesh here, the outer mesh, we see that has no current sources in it in the circuit. Therefore we can and must write an equation for that one also. So we'll select I1. And this time we're going to go in the direction of that mesh current, which means this time going counterclockwise. So let's start at the lower left here. So our first term is going to be a fixed voltage, and then we have another term of the same form. So we'll take 2 of those terms. We could use 1 term and just mentally add those 2 values. That's also acceptable. Then we have an impedance here with 2 mesh currents, so that will require this type of current for the voltage drop, or this type of term rather for the voltage drop. And then lastly we have an impedance here that has only 1 mesh current because this mesh current is defined to be 0. So that will require this type of term, which is 1 mesh current. And then that's back to the starting point, so that must now be equal to 0. So now we'll go ahead and fill in the blanks. So here we're encountering the minus sign first as we go counterclockwise for the V2S, so that we'll need a minus sign in front of the value, which is the V2S value is just 2 over S, so 2 slash S. And then next source, we're again encountering the minus sign first. So this is actually a voltage rise, and remember we're adding voltage drops going this way. So because this is an actual rise, that means it's a negative drop. So once again, we have a minus sign, and then that's going to be the V1S value, which is 6 over S. And as I said, we could have just entered 1 term with minus 8 over S, but I'm just doing it this way. Then we'll have this one. We have the I1 current minus the I3 current for this impedance, since the I3 is going the opposite direction here. It's going clockwise. And then we just enter the impedance value, the 1 over parentheses 3S, in the parentheses essential. And then finally over here we have just the I1 current going down through that for the drop there. Oops, 1. And also I'm using the tab key here, by the way, to go among these text boxes quickly. And then here we'll have the 5 ohm. So now we can check that equation. And once again, that KVL equation is correct. So now, because we do have a dependent source here, the 6ix source, we need to write a separate equation for the control variable of that source, namely this Ix current, which points up through the 5 ohm. So we're going to select control variable equation. And again, we need Ix, so we pick that term for the name of the current, and then it's going to have just one mesh current going through it, which is I1. Again, the other mesh current here is 0 because we chose that as a reference mesh, just like if you choose a reference node, say nodal analysis. So this will be the I1 current here, and this will be the Ix. And then notice that because Ix is actually pointing in the opposite direction to I1, we need a minus sign here. Or we could put the minus sign on the other side, it doesn't matter, but just one minus sign. Okay, so we'll check that. And then finally we need our sought variable, which is this V0 voltage across the 5 ohm resistor. So we'll select sought branch voltage because that's across a single element. And that voltage is called V0, which is pre-filled for us here. And then that's going to be, again, one mesh current times that impedance because there's only one mesh current through that element. So we take this term. And then we notice that the I1 current is actually going into the negative side of that voltage, which is active sign convention. So we need to have a minus sign. Remember that the Ohm's law-like equations often have a minus sign depending on the polarity. So this will be I1 minus I1 times the 5 ohm. So again, always check the polarity of all these terms. Otherwise, that could result in errors. Okay, so we'll go ahead and check that. And that is correct. So now we've entered all the equations, and notice that we have 1, 2, 3 mesh currents, but we also have a control variable Ix. So we have a total of 4 unknowns here. But we have, in fact, 1, 2, 3, 4 equations involving those 4 variables. So that's now correct. We have enough equations to solve. We're not counting the sought variable equation as that's sort of separate. Okay, so now we can safely click No More Equations, having checked the number of equations. And now it's going to ask us to combine these coefficients and enter these equations in simplified form. And we're allowed to clear fractions and things if we need to do that, although I won't probably bother to do that in this case. But we certainly could. Okay, so now I'm going to show this on paper here. So the first equation is very simple. It just says I2 equals 6Ix, or putting everything onto the left-hand side, that would be 1I2, and then we have minus 6Ix, and then that's going to be equal to 0. And here I have to use the scroll bar to scroll over a little bit to see the 0 there, but that's already 0. Okay, that's the first equation, which is very simple. And let's do the fourth equation, which is also simple. So that says Ix equals minus I1, or in other words, Ix plus I1 equals 0. So here we'd have a 1 there. And then we'd also have a 1 for the Ix. And then that's already going to be pre-filled as 0 over here. Okay. Now, these other two equations require a little bit of algebra, perhaps. And so this equation here, I'm going to take these two terms and combine them. So that's negative 8 over s. And then that's our constant term in the sense that it does not involve any of the currents that we're solving for, namely I1, I2, I3, or Ix. So we can bring that over to the right-hand side in standard form. So I've written that over here as a single 8s term. And then I look for all the coefficients of I1, and that would be 1 over 3s. And then we also have a 5, so 1 over 3s plus 5. And then the coefficients of I3, well, that only appears once, so the coefficient would be minus 1 over 3s. Don't forget the minus sign there. And so I've written that here. I've factored out the minus sign. And now, to put these coefficients in standard form, I do need to put them over a common denominator anytime we're adding fractions like this. So we'll multiply, obviously the common denominator is just going to be 3s. So we multiply the 5 by 3s over 3s, giving us 15s, which I've written here to begin with in the first term. And then the 1 carries over down here. And we can, of course, check that the 15s over 3s is 5, and the 1 over 3s is 1 over 3s. And now I'm going to take advantage of the fact that I see an s in the denominator of all three of these terms. Therefore, it would greatly be advantageous to just cancel that out right now and simplify the further equations that we have. Okay, and so I can go ahead and enter that now. Or I could rationalize it further, actually, if I wanted to. But let's go ahead and enter it right now. So we're going to have the I1 times 15s plus 1 divided by 3. And then there's no I2 terms. That's left at 0. And then this is going to be minus parentheses 1 over 3s. Oops. Now. Okay. Actually, let's see. Let's just leave out the parentheses there. I don't really need that parenthesis. I'll just put minus 1. And then I need the parentheses around the denominator. Otherwise, I'd have to put square brackets in there to enclose parentheses. But I don't really need that first parenthesis anyway. So I have minus 1 over 3s. And then the right-hand side of that equation now needs to be, oops, needs to be 8s. I'm sorry. No, we've canceled that, so it just needs to be 8. Okay. And then we'll go to the next equation, which is this one. And I've rewritten that here. And again, the constant in this equation that doesn't involve a current is going to be the 6 over s term. So we bring that to the right side by subtracting it. So we have negative 6 over s here. And then we look for the coefficients of I1. So that's just going to be the negative 1 over 3s. So that's the first term. And then for I2, we have minus 2s is the only place that appears. So we've written that here. And then for the I3 term, we see we have two terms. We have a 2s here, and then we have a 1 over 3s here with the plus sign. So we have 2s plus 1 over 3s times I3, and that's equal to our constant. And now we need to put that over a common denominator here. So we carry over these terms, and the 2s plus 1 over 3s, the common denominator, of course, will be just the 3s. So we multiply this by 3s over 3s, so we get 6s squared plus 1 divided by the 3s. And that's our term there. So we can enter that now into the system. So scroll back over here, and the I1 coefficient now is going to be negative 1 over 3s. Get rid of the 0. Again, using the parentheses in the denominator, then the I2 coefficient here is going to be minus 2s. No parentheses needed there. And for I3, then we have the parentheses 6s squared plus 1, plus 1, divided by the 3s term. So again, we have to put parentheses in the bottom. And again, I need parentheses on both the top and the bottom here to make sure that everything is properly divided, and the s squared is denoted that way. And then the right-hand side of that is the negative, there's no ix term, and then the right-hand side is negative 6 over s. Okay, so that completes our 4 equations here. So we'll go ahead and check those. Oops, so I may have made a typo there here. So let's check that one out again. So that was the equation up here. So we had 15s plus 1 over 3 times I1, and then we had a negative 1 over 3s times I3, and that was equal to 8. Let's see here. Okay, not seeing where the error is there. I forgot to cancel that. I put in an S here where I didn't mean to put that in. Okay, that was the problem. So I canceled that S. So -1/3 simply. Okay. And that's also been converted to a decimal, and that's now correct. Okay. So now we need to put this into the matrix, although we're not going to really use the matrix here, but just to keep the program happy, we're going to copy that from the simplified equations. We can just use that button. We could multiply through if we wanted, but I'm just going to check it. And of course, that's correct. So now we need to solve these equations. So it gives us the instruction to retain our solutions. I'm going to have to do that on paper. Now, it's asking us to enter I1, I2, and I3, and you can do that if you wish, but it's going to be some extra work here, because if we look at what we're really after V0, and V0 depends only on I1, so we don't really need I2 and I3, and that would take extra work to calculate those two. So in this case, I'm going to just elect to skip that, because it's not really going to help me any, and finding V0 is pretty simple from I1, so I'm just going to skip this. If you want to do it, you certainly can, but there's no real need to. So now to enter V0, I'm going to calculate that on paper, and it does inform us that because we're going to be doing a partial fractions expansion on the SOT variable, that we do need to factor any quadratic terms in either the numerator or the denominator when we enter them here. So they need to be entered in factored form. If we don't do that, it'll just tell us that we have to do it. It won't charge an error, but it will remind you that you need to factor those. So we may as well just do that to begin with. Okay, so now we have to do some algebra in order to solve our system of equations. So again, we had this equation here, and we had this equation here marked 2. This is marked 1 and 2. And we also had that I2 is equal to 6ix, and we also know that ix is equal to minus I1. So we can really combine those two together. Just we want to get rid of ix really, so we'll just substitute that in here. It doesn't appear anywhere in this equation, and so that just gives us I2 is minus 6I1 when we combine those two equations together. And then we can basically combine that with the other equations. We always want to take these simple equations and put them into the more complicated KVL equations. Again, solving this using matrices is not something I would recommend. I think you'll find that that's much lengthier than the process I'm going to show you here, and therefore probably more error prone as well. So basically what I'm going to do is take this equation here that we had before and substitute in for the I2 equals minus 6I1, and then that basically is going to combine with the I1 term here. So I have I1 bar now times minus 1 over 3s, and then when we put in the minus 6I1, that's going to become 12 plus 12s multiplying the I1 here for this term. And then I have the I3 term here, and the remainder is the same. Now I need to combine these to make a proper rational fraction, or I'm sorry, just a rational fraction, a rational function rather. It's not actually proper. And the common denominator there will be 3s. So I'll multiply this term by 3s over 3s, so it'll give me 36s squared, which I've written before the constant, and then minus 1 from here, and then that divides by 3s. And of course we can divide those out to make sure that we still have the correct values, which we do. And now, once again, we notice that there's an s everywhere in the denominator, so it would behoove us to simply cancel that out. So I've crossed out the s's there. And now we can rewrite this, and also, since we've got 3's in both of these terms, it probably makes sense to just multiply through by that to make the equation a little simpler. So I've written here as I1 times 36s squared minus 1 plus I3 times the 6s squared plus 1, and then just multiplying by 3, this becomes negative 18. Okay, so that's a simplified form of this equation 2, and then we'll take equation 1, which was up here, and there we don't need to substitute I2 because it doesn't have one, but I will again multiply through by the 3 to simplify that, so I'll have I1 times the 36, I'm sorry, I1 times 15s plus 1, I mean, minus the I3, and then this becomes 24 when we multiply through times the 3. So now we have our two equations we want to solve, and a simple way, I mean there's many ways of solving this, but remember that we're after because our sought variable depends on I1, we're really after I1, not I3. So let's get rid of I3, and a simple way to do that, obviously, is just to solve the second equation for I3. So we just bring the I3 over to the right, bring the 24 over to the left, and we have I3 is I1 times the 15s plus 1 minus 24. And then we can just plug that into this equation, which will eliminate I3. So we have I1 times the 36s squared minus 1 plus, now the I3 becomes the first part of it becomes I1 times 15s plus 1 times the coefficient here. And then the second term will be this constant minus 24 times, again, the coefficient here. And all that's equal to negative 18. So now we just need to solve this for I1. So we'll collect all the things that multiply I1. So first we have the 36s squared minus 1. Then multiplying out these terms, the 15s times the 6s squared will give us 90 times s cubed. And then we have a 6s squared here. And then multiplying here, we have a 15s. And then the constants multiply to give us a plus 1. And then because this is a constant term in the sense it doesn't include I1, we'll bring that over to the right-hand side where it belongs. And so that becomes a plus 24 times 6s squared, which is 144s squared. And then, again, distributing in to simplify that, that'll become plus 24. Now, we'll notice that the minus 1 and the plus 1 cancel out, which is great because that means we won't have to actually work with a cubic equation here. We can, in fact, simplify it to be quadratic by factoring out an s. So here, we'll solve for I1 just by dividing by these parentheses. And we'll also simplify the right-hand side. So the 24 minus 18 is 6. And then we have the 144s squared. So that's the numerator. And then the denominator now, factoring out an s, is going to be 90s squared is the first term. And then the 6s squared and the 36 gives us a 42s squared. And then factoring out the s gives us 42s. And then the 15s by itself, factoring out the s, just becomes 15. So we have this s factor now. And that's our I1 in fairly simplified form. And now, since we're computing V naught here, we need to multiply that times minus 5. And so I put in a minus 5. And I've also decided here to factor out a common factor of 6 in these coefficients, which will help simplify things. So we brought a 6 out here, leaving it as 24s squared plus 1. Again, dividing each of these constants by 6 and bring it out front. Then we also, I'm going to bring out a 90 out front in preparation for the factoring. So we're going to bring out a 90 here in front of the s, then that becomes s squared here. Then we divide each term by 90, so 42 90ths is 0.4667 times the s, and then the 15 divided by 90 is 1/6, or 0.1667. So now we've put it in this form. And then I'll just combine the constants. This gives us a negative 30 divided by 90, which is negative 1 over 3. And then we'll leave this as 24s squared plus 1. And then we have just now the 3 in the denominator times s, and we have that now in a form where the coefficient of s squared is 1, which is very convenient, really, for factoring. So I always like to make that coefficient of the s squared term 1. You don't have to do that, but if you don't, then you need to be careful when you do the actual factoring process. So now, because this does require a factor to form, we have to find the roots of this quadratic in the denominator. And so, again, the quadratic formula, if we have ax squared plus bx plus c, the preferred form for that is x equals negative b over 2a plus or minus the same thing, squared minus c over a. So here, the b is 0.4667, so minus that, divided by 2, plus or minus the square root of the same thing, quantity squared, minus the c, which is the 0.1667, the a here is 1. And this just evaluates to minus 0.2333, and plus or minus, and now we notice that this is actually going to be a negative number, so we have to factor out a j. And of course you can just do it on a calculator too, it'll do that for you. But that works out then to be plus or minus j 0.3350. And the units of s are always inverse seconds because, again, it's a complex frequency. So having done that, then we can rewrite our expression here in factored form. We don't really need to factor this numerator because there's no linear term there, so it won't require that. So we have negative that quantity, and then we have the 3s, and then now remember that because we have to make sure that this is actually a root, so we have to take s plus the 0.2333 minus the j, this term, for the first term here. And again, that's so that when we substitute in the minus 0.233 plus that j value, that will actually give us 0, as it should. And then the second term, we just changed the j to minus j, so it's otherwise the same, but the j becomes here positive. Okay, so that's our fully factored form of the expression. And now I'm going to enter that into Circuit Tutor. So I'm just going to write minus parentheses 24s squared plus 1, close the parentheses, and then I divide by the denominator. Now I'm going to have to use a square bracket to enclose the other parentheses in the denominator. It won't allow me to use parentheses around parentheses. So I have the 3s, those don't really need parentheses, times the s plus 0.2333 minus j 0.335, and it's really a 0, but I left off the 0. And then we have the s plus 0.2333 plus j 0.335. Now notice, so I'll complete the parentheses and the closed brackets on the denominator. Now notice I am doing all of this to 4 significant digits. Again, there really should have been a trailing 0 on this one, but I just left it off for brevity here. And it is important to have accuracy here. And again, it's significant digits that matter, not the number of places after the decimal point. So here, for example, for 4 digits, I really need 0.3350. I just omitted the 0 here for brevity. Okay, so we'll now check that equation. And that is correct. And so the next step is going to actually do the partial fraction expansion. Okay, so we can scroll down to see our results that have been printed at the bottom. I'm going to select the only option here, which is partial fraction expansion. Unfortunately, I need to scroll back down. Okay, so now we're going to carry out the partial fraction expansion here. So I've done that on paper. So we know we're going to have basically 2 terms. The first term is going to be just a constant. Well, we'll put the v naught equals first, and then we're going to have that term. I'm sorry, actually, no, for partial fractions, we're going to have 3 terms, right? We need all 3 of those terms. I was thinking ahead to the time function. Okay, so because these are voltages, we all have voltage units here. So I'll put that in now. And then the first term, well, we need to calculate the coefficients. So I've done the expansion here on paper. So this will be, since we have poles at 0 at the origin, and then at minus 0.2333 plus j 0.335. So we'll have a over s, the first pole, plus b over this term. And then we're going to have plus b conjugate over this term. Now it's very important that I choose the term here that has s plus alpha minus j beta, where alpha and beta are positive numbers, and call that b as opposed to calling it, say, b conjugate, which I also could have done. But if I pick the wrong term there to do when I do the inverse transform, I'm going to get the wrong phase angle. So I need to carefully identify what's b and what's b conjugate here. And that's a common mistake that people make, is picking the wrong term. Okay, so now we simply need to evaluate those coefficients, and we really need only a and b, because the b conjugate will take care of itself. So to find a, I'm going to use the heave-aside or cover-up method, where I multiply through by s to both sides. That will cancel out the s here. And in fact, for finding the a, I'm actually going to use the unfactored form up here, because that's a little easier. So it'll actually cancel out this s. And then we set s equal to 0. And now we have an s term here and here, so that's going to make those terms go away when we set s equal to 0. And then here, again, by setting s equal to 0, I'm just going to have a negative 1 on the top, because that term goes away. So we have negative 1. And then here I have the 3. The s is canceled. And then I have here, these first 2 terms go away, and I just have the 0.1667. So that saves me a little bit of work as opposed to using the factored form, which is not necessary here. And then just evaluating that, of course, that's just negative 2. Now to find the b coefficient, now I have to use the factored form. And so I'll multiply through by its denominator, the s plus 0.2333 minus j 0.335. And that will put that term in here, and then I'll set s equal to negative 0.2333 plus j 0.335. And that makes this term go away and this term go away, and this one just becomes b. So that makes it very easy to evaluate b. And so we'll just take this expression here. So we have the negative on the outside, then a 24 multiplying the s squared, which is now, again, that value I just said, which is what we're setting s to. That gets squared. We add 1 to it. And then we divide by the 3. And then here's the s again, substituted for this. This term's now canceled because I multiplied by it. And so I just have this term. And so that's going to be the s value here, again, the same value, plus these two constants. And notice then that the real parts are going to cancel out there, and I just have the imaginary parts, which are both the same. And so now I can just enter that expression directly on a calculator that handles complex numbers, and that will evaluate out in rectangular form to -3 minus j 3.483, which I do need the rectangular form to enter in Circuit Tutor, but I actually really want the polar form when I go to do the inverse transform, so that's going to be 4.597 angle minus 130.7 degrees. Now, notice if you're doing inverse tangent, which you probably shouldn't be because it's much easier to use the rectangular to polar conversion, that you would have to make sure you're in the correct quadrant here. This is going to be in the third quadrant because both these values are negative. And so anytime the alpha or the real part is negative, you're going to have to add or subtract 180, which I've already done here. In fact, the calculator just did it for me. Okay, so now I'm going to enter the coefficients here. So this is going to be, I could just put the minus sign out front, and then that's going to be the 2 divided by the s, because that's the a over s term. And then the next one, this coefficient is going to be the -3 minus j 3.483. And then that's divided by the s plus 0.2333 minus j 0.335. And then this is going to be, actually I could just copy these over and change the j to minus j here. Should be a little easier instead of retyping everything. So I'll just make that now a plus sign there, and then make this a plus sign there. Okay, so that should be correct, hopefully. And so we'll just check that. And that is correct, and it's been printed on the screen. And since now we've done all the partial fractions, we just click No More Equations. And it tells us that we're going to have to do the inverse transform as the next step to go back to the time domain. And we'll select the inverse transform. That's the only option here. And it's going to remind us that we do have 2 sets of terms, and you will sometimes need that second set, so you can see it there. But here I think we'll just need these terms here. Okay, so I'm going to scroll down just to see our partial fraction expansion where it's been written here. And so now we want to find v naught of t. So I'll select the SOT variable there, equals. And now, because I'm going to have to enclose, or multiply everything rather, by a unit step function, I'm going to enclose everything in brackets. So I'll put a left bracket, and then we're going to have a constant term, or a u of t term really, from this term. So we'll put in a constant. And then these 2 terms, as you may remember, will give an exponentially damped sinusoid. So that's this term over here. So I'll click on that, and it's going to remind us that we need to have the coefficient there be positive in front of that, just to get the right phase angle. And then I'll close the brackets and put in the unit step function and put in the proper units, which are again going to be volts. And if you didn't remember that that's the inverse transform of this expression, you could, of course, use the Laplace transform table, which is shown here, and that would be the last entry in this table. So basically the inverse transform of this type of thing, basically, which is the form that we had, is going to be this, which is the term type that I've entered there. Okay. Okay, so now I just have to fill in the blanks here. So the constant here was going to be our -2. And that's multiplying the u of t on the outside due to the bracket. And then the coefficient here of the exponential, that's going to be twice the magnitude of b according to that formula, which I've covered up now, but it basically needs twice the magnitude of that. So I've taken this magnitude, the 4.597, and multiplied by 2 to give me 9.193. Again, that's based on the formula in the table, which just to remind you of that, it has twice the magnitude here, times e to the minus alpha t cosine of beta t plus theta, where theta is the phase angle of the constant, which we're calling b. Okay? So we always have a decaying exponential, never a rising exponential, because that would be an unstable system, and these problems are not, I mean, it could be unstable with a dependent source, but this one is not, and we typically won't give you that type of problem. And because instead of e to the minus alpha t here, we need a time constant in the denominator, so I have to take the reciprocal of the alpha to get my tau. And so the alpha, remember, is this coefficient, the real part here. So that's the 0.2333, which is inverse seconds. Take its reciprocal gives us 4.286, which is our time constant in seconds. It doesn't have to be entered that many digits, but I'm just going to do it anyway. And the beta now is the imaginary part. So that's the 0.335. That's the radians per second. And then the phase angle, again, is the phase angle of the b coefficient, which is where that comes from. So I'm going to put a minus and then a 130.7. So that should be the entire thing. And so we'll check that. And that is correct. And now we've basically done everything. So we just click no more equations. And it is going to go ahead and generate the PDF transcript, as always, of your work, which you can use to review later by clicking on Review Work. Now, if you'd like to see more details here, you can request that if you want to just review a little bit how everything was derived. Okay, so I'm just going to blow that up there, and it shows the conversion from the time to the complex frequency domain, and then it's highlighting the different equations and how those terms are derived from the KVL by basically doing a path around the circuit there. And I could view each of those equations, and also all the results are shown down here. Now, you also have an option to get explanations of any of the types of equations if you're unsure about them, to review the Laplace transforms, and also to show the steps involved in a Gaussian elimination. I'm going to show this just as a matter of interest, to show you how complicated it is. It takes a little while to plot here because there's so many steps. And so you see that doing this really probably would be considerably more work, especially since a lot of the algebra isn't actually shown here that you would have to do. You'd have to go through a lot of steps. So this is why I do not recommend the Gaussian elimination. Rather, the simple substitution process I showed you, I think, is considerably simpler. Okay, so I'm going to go ahead and erase that now. And that completes the level 2. You can review your work here, and you'll also be asked to complete the survey. And that concludes the example.